Well, my student, today we shall pass on to the second part, which is the main part. So we are going to part 2. The Boltzmann equation and relaxation time. Approximation. So today we are now going into the main part of our discussion. Actually, in our last class we noticed that when an electron moves through a crystal, two opposite mechanism comes into play. So two opposite mechanism that comes into play when the electrical conductivity or the flow of electron inside the crystal is concerned. And the two mechanisms are, one is the driving external force, and secondly the dissipative scattering event. So these two opposite mechanisms is essential that will come essentially during the flow of electron. Now, the Boltzmann equation plays a very important role. The interplay of these two opposite effects will nicely managed or discussed through Boltzmann equation. Describe in Boltzmann equation. We will say this definitely, but I am just highlighting what will be there in our today's discussion. We will also see that the Boltzmann equation actually gives non-equilibrium distribution. So the non-equilibrium distribution will be given by the Boltzmann equation. So our tutorial objective to find out the non-equilibrium distribution, right? So let us see how we can do that. Now, in absence of in absence of external field, we can expect, and it is the usual situation, that all the particles, they remain in thermal equilibrium, and that equilibrium distribution can be described through FD statistics. So in equilibrium, in thermal equilibrium, the distribution F0 with, say, energy value E at energy E is expressed as 1 by e to the power E minus EF. EF is the Fermi energy divided by kT, K for Boltzmann constant, plus 1. So this is the equilibrium distribution. Of course, we should keep in mind that this distribution is independent of position R and time. And also, this is valid irrespective of collision. So even if there is no collision, no phenomena, then this is valid, and this is your the equilibrium distribution. We all know about this, but we should keep in mind that this factor, the function, is independent of R and T. Now, when there will be an external field, what will happen? This thermal equilibrium will be disturbed, and the situation will go over to a non-equilibrium situation, right? So, in presence of external field, what will happen? The equilibrium situation goes over to non-equilibrium. And our main objective is to find that how this distribution, the equilibrium distribution, will be transformed to a non-equilibrium distribution. So, in presence of this external field, that F0, the equilibrium distribution F0, you may call it, we can refer it by K also, which goes to F K. But here we have to keep in mind that as the situation becomes non-equilibrium, so it cannot be independent of the position of the electron and the time. Actually, with time, there will be some phenomena or the situation will be different. So time varying situations is there. So at the same time, as there will be F, so F can be now have a dependence over R and T. So our objective is to find this non-equilibrium Ft. This is the equilibrium F0. We shall pass over to find out the non-equilibrium field. Now, the non-equilibrium function can be obtained. We will try to get that in two steps. Firstly, we consider the effect of field and then we add up the collision effect as a correction. As a correction to the previous. Correction to previous. So how it can be done? Let us see. So now we consider the external field. Maybe in general as a Lorentz type of force. So under the presence of this field, what will happen? Let us try to gaze and try to assume what can be there. Now, as we move from a equilibrium situation to non-equilibrium situation, at any time, at any instant, t, let the position, let the particle be specified by the coordinates, say r, let k first, by k, r and t. Now let us think, and mentally we can imagine the situation in such a way that we are now at this very instant of time t, where the particle is specified by this coordinate. Now, we can easily expect that the present instant t has come from an earlier instant, and say at a very small infinitesimal time earlier, what the situation will be. So next imagine at an earlier time, say at t minus dt, what will happen? That r will go to r minus dr, also k will go to k minus decay, and time t was t minus dt, right? So this is the earlier positions. This is the present position at t. So at an infinitesimally small time earlier, the position, the coordinates can be defined in this way, and this can also be written as r minus v dt. This can be written as k minus f dt by h cat, and t minus t will go, right? Because it is very obvious to you, and I think you can do it very easily. So in absence of any conditional phenomena, so in absence of condition, if RKT can be related to the previous distribution in this way, R minus Vk dt, K would be transformed into K minus F by H cat dt, and T was T minus dt. Now, if we consider the conditional term, which is the time varying part, so if we consider the scattering effect, which is the time varying, which may be time varying, and can be written as in this way, say del f del t scattering into dt. So the correct form where both the effect of scattering and the external field is taken into consideration. So correct form looks like f of r k t can be written as f of r prime k prime t plus del f del t s for scattering dt. So this is your expression, this was expression 2 and now let it come expression 3. Right. Now let us have a physical meaning of these two expressions, mainly the equation say 2. Now we find that in equation 2 that if at a time instant t is equal to an earlier time instant t minus dt. So it necessarily implies, implicitly this relation indicates that there must have some local equilibrium. So whenever a system of particles passes from one time to another time under the influence of external field, the distribution pattern will remain same. There will be no change. The pattern is differing from the thermal equilibrium. Now the situation is that non-equilibrium point, but yet in this non-equilibrium situation also the distribution pattern at some instant of time will be same to its earlier instant, or we can say at a later instant too, if the time gap is very, very infinitesimally small. Now let us have a mental mapping, let us have a pictorial view mentally. So for this, I like to erase this portion from the board. Of course, in equation 3, it should be t prime, right? And if we write it here in full form, it would be r minus vk dt k minus f by h cut dt, and t will be t minus dt, right? Plus the scattering term. Well, now imagine that you are given a large section of a crystal lattice, and within that we are concentrating our attention to a very small region, very elementary volume, say having wave vector k prime at an instant specified by this positional vector r prime. Now from this situation, where some of the states are occupied and some are empty, let it be such that some states are occupied and there are some empty space also. After an infinitesimally small time gap delta t, let it came to a new configuration in hyperspace where r prime now became r and your k prime now become k. But the interesting fact is this, that even under the influence of external field, the electronic distribution would remain same. Electronic distribution would remain same as it was in earliest point of time. So under the action of the, say, external field F, so that particular section of the the molecular electron has changes its position, has a shift due to the application of the field, as well as it has a changed configuration over its momentum vector or wave vector k. So this is the actual fact that is happening. But keep in mind, but you look at this point, that the distribution F here is your F r prime k prime, and the distribution here is the F of r and k. All are same, both are same. So this is the actually what happens when electric field or any external field is applied. The configuration of the particular section of electronic collection of electrons can be represented in this way. So it is called that it is implicitly assumed local equilibrium, which gives us that F at time, say, t minus dt is equal to F at t. Right? So it is a local distribution, the implicit reaction. This thing also we can picturize in this way, that r prime, k prime, t prime is r, k and t. Now this thing can also be presented in this way. So for, let us assume that at t equal to 0, at an instant, at t, and at an instant of t minus dt, say the distribution is like this. So after a time interval dt, the distribution is shifted to some other position, say under the application of the field. So it is your F having your electron, I mean within the displacement of the electric field, set it will be the K, and it is your K minus F by H cut dt. Right? So there is a just shifting of origin, but no change in pattern. So this is the physical implication of the expression 2, as well as, of course, for expression 3 there is an extra term. We are going into that point later. So presently for the expression 2 we can have this pictorial view mentally, right? Now let us have a relation for time derivative. I mean, then let us find the rate of change of distribution here, that is for non-equilibrium. To have this, we can make a time derivative from this equation 3. We can write easily. So from 3 del f del t equal to this much. I mean, it can be written as del f del t at the final. Oh, cancel it. From expression 3, we can write easily the del f del t minus plus equal to Vk minus Vk into del R of Fr, del R of F plus, I mean minus F by H cut into del K of F, right? And there is a scattering term plus del F del T scattering. But we have written in three-dimensional form. It is the delta operator, or we can write it in this way: del T plus Vk del R of X plus F by H cut del del of k f equal to, so changing the sign, you can have a del del f by delta t scattering. Okay, let it be equation number 4. Now this equation is the final expression for your Boltzmann equation. Now this relation is known as Boltzmann transport equation. Boltzmann's transport equation. Because the Boltzmann's equation is associated with the transport of charged particle or the electrons. Now, this equation, the terms of this equation can be identified in this way. The left hand side is known as the drift term, and right hand side is the scattering term. So this term arises out of the applied field. So the drift term arises out of external field F. The interesting fact is this, that the drift term, which is caused by the external field, is balanced by the scattering term. Balanced by the scattering term. The scattering effect of term that is on the right hand side. So this is the physical implication of the equation, that whenever an external field is applied on a crystal lattice, the thermal equilibrium of the electrons will be disturbed. So the system will pass from a thermal equilibrium distribution to a non-equilibrium distribution. And we are talking about that non-equilibrium distribution function f. And that external field mainly causes the shifting of the particle and also have a change in momentum, I mean the K factor. And this term, the left hand side term, is known as drift term. So external field causes some drift factors, and that drift factor is assumed to be balanced by the scattering factor, right? So this is the interesting point of the Boltzmann transport equation. Now we can also specifically call the parts of this left hand side in this way, that this is called the diffusion induced effect, and it is called the field induced effect, right? So these are the, specifically we can distinguish the particular terms, what are they mean, right? So we are now arrived at the main discussion point, or we have arrived at the derivation of the Boltzmann equation. Now, one thing has to be considered here, that the scattering term, which we have told you earlier, that is very complicated. Sometimes it poses very formidable problem to solve it analytically. Here also, that problem is there. So we have to make some assumptions so that we can tackle the scattering term in a simpler way. And that will be done by some approximation, and that approximation is the relaxation time approximation. So now, after arriving at this point, we will pass over to the relaxation time approximation. And we should keep in mind that approximation is necessary for tackling this part only. Okay? Now, before going detail into the relaxation time approximation, let us discuss a very little about, or just to recollect what I have learned about the scattering term. So now we shall discuss a very little about the scattering term, how it can be expressed, how it can be managed quantum mechanically, and what is the functional form of this. After writing that, we will pass over to the relaxation time approximation, right? Okay. So now I like to discuss something about the technique or the mathematical ways to tackle the scattering effect. In our last class, we have discussed elaborately that the transition probability, I mean the scattering probability, specifically it is the scattering phenomena. So the scattering probability Wk prime k is almost equivalent to the square modulus of k prime h prime k square. So the scattering probability for what? To have the scattering, to scatter from a state specified by k to a state k prime, right? So this is one point we all know about this. Now the question, that what will be the total fraction if this distribution, if this scattering probability is to calculate, then we have to keep in mind that distribution function has an important role. Because how many particles are there in a particular state or a set of state, and from that state where they are going, is there any possibility to go there? If all the states are occupied there, then no one can go. If there is partly vacancy, someone will go. If all are vacant, then every particle can go. So there are an important role of the distribution function to estimate the amount of scattered particle. So for scattering from test state, we need distribution leveled by k, right? We are not writing the vector form also, there is all vector. So if the scattering starts from a state k, we need the fraction or the distribution of the electron in that state. So this F is necessary to start scattering, and to go to some other configuration, say k prime, we need fk prime. We need fk prime. But mind it that fk prime is the number of particles that being occupied. So it indicates the occupancy. Occupied. But the particle when want to go from one state to the other, that state has to be vacant, otherwise it cannot go there. So in order to go to some other state k prime, we need unoccupied distribution of states, that is 1 minus fk prime. So there are two factors. One is that how the particles are distributed at the starting point, that will be defined by the fk, and how many states are there fallen vacant so that they can pass over there. So we need the unoccupied fraction of the second configuration leveled by k prime. Is it clear now? So to have over a volume V, we can write integral decay V by twice pi cube into say W K prime K with Fk because of the starting configuration. It will pass over to the final configuration, and that can be written here as 1 minus K prime. So for a volume V, we need to estimate this much factor for having the amount of particles or the fraction of the particle that has been scattered from a configuration Fk to Fk prime, right? Well, now let us write the scattering term explicitly. In a conventional or in more general form. So the scattering term can be written in more general form in this way. Minus right? Here the first term indicates scattering from an occupied state K level by K to some unoccupied state level by K prime of course this occupancy and unoccupancy is marked by your Fk, and this occupancy by this, and this unoccupancy by 1 minus F K prime, right? So in this way we have written this first term, and the second term is just the opposite. it is just the opposite to first term, to first event, right? One thing more we have to take into account in this expression, that why we have taken simultaneously both these two types of terms in a particular scattering event. For this, we again let us think a particular domain. There are two particular domains, say it is K, it is K prime. So electron from K prime can scatter to, electron from K can scatter to K prime. Now, in doing so, it may also happen that some particle may scatter from that K prime state. So, for the K prime configuration, what happens? Someone is coming in and someone is going out. Is it clear? So, simultaneously for a particular domain, there is an influx and an outflux. So this is called, this first term is called the influx term, influx or scattering in, and this is your outflux or scattering out, right? So these are the meaning for this two expression, and let the equation for this scattering term be labeled by equation number 4. Okay, this is the most general form of scattering term that we have written here. Complication is still there due to the integration of these factors, and for that discrepancy, for that difficulties, we shall now pass over to some approximation method, that is your relaxation time approximation. So we are now going to pass to our next topic, that is your relaxation time approximation. Well, so our next point of discussion is the relaxation time approximation. Relaxation time approximation. We have discussed already that the scattering probability, that is a W K prime K, is such a relation which is a complicated integral differential equation let us discuss about the relaxation time approximation. In our last discussion, let us now discuss about the relaxation time approximation. I have told you that in non-equilibrium situation arises out of the application of external field. The situation may come back to its equilibrium distribution by way of scattering phenomena. And in evaluation of scattering phenomena, we came across a quantity which we call WKK prime as the scattering probability. And this factor is very complicated. It is an integral differential equation that we have to solve. Now, in order to avoid the analytical part of to get the solution of this term, this relaxation time approximation is proposed. This approximation actually it tells the rate at which a distribution F returns to its equilibrium distribution is proportional to the negative deviation of the function, distribution from its equilibrium. So rate at which the change occurs, and this is nothing but the scattering term. So returns to its equilibrium distribution is 0 due to scattering. Okay? This is the proposal of relaxation time approximation. And this can be written as minus F0 by a characteristic parameter which is called the relaxation time. This term is a characteristic time and it is called relaxation time. So relaxation time means that is the time at which a system at its non-equilibrium state can come back to its equilibrium distribution via scattering phenomena. Okay? Now, if we now integrate this term, then we can find some interesting point. Now, let us integrate. So, integrating the term in this way, that is df divided by f minus f0. I will limit at t equal to 0 to t as it is minus integral 0 to t dt by tau. Right? Now obviously this will gives us f minus f0 at time t divided by f minus f0 at t equal to 0 is equal to e to the power minus t by tau. Right? Now rearranging this, or f minus f0 at t equal to f minus f0 at t equal to 0 e to the power minus t by tau. Now one thing is to be careful that it is the deviation at a time t. This is the deviation at time t equal to 0. That means at the time of onsetting the switch off condition of the external field. So it is the time t equal to 0 means, so t equal to 0 means the instant at which external field is switched off. Okay. Now for this specific point, the f at t equal to 0, at t equal to 0 is the distribution may be referred as the stationary distribution at the moment of switching off. Right? So this A at t equal to 0 can be written as the stationary distribution at t equal to 0. Okay, so this is the point to be noted, that this f and that f are not always refers to the same physical situation. At the time of onsetting the switching of condition, there is a stationary distribution already attained as a effect of external field, and that distribution is referred as F static. But whatever be it is named, but we can make a simplifying relationship in this way, that let us define, or if we define G as, of course, G of K as the deviation f minus of 0, right? Then this relation would look like at t as gk 0 e to the power minus t by tau, right? So this relation tells us that the deviation of the distribution function, from its equilibrium value, it decays exponentially with time, and this decaying factor arises out of the physical processes, which is called the scattering process, right? So what I'd like to emphasize here is this, that the process of scattering facilitate a non-equilibrium distribution, facilitate the non-equilibrium distribution to come back to its equilibrium distribution, I mean thermal equilibrium distribution, via distribution, right? And this is attained at the time for the process, and this indicates that tau is that time. Okay, so relaxation time is nothing but the time through which and stationary distribution which is attained due to the application of field, and when that field will be withdrawn, that distribution will go back to its original, I mean equilibrium, thermal equilibrium position via a physical process which is called the scattering process. Now this time tau is in general is a function of R and K. It may not be, I mean it should not be a constant value. It must depend on how much the deviation is created. That means it depends on the strength of the application of the field, the strength of the field, and also on the distribution on the local distribution of the configuration, I mean the electronic distribution, it may be homogeneous or non-homogeneous. If it is inhomogeneous, then this tau must depend on R. If it is homogeneous, then the dependence of R will not be there. So in general, the characteristics time, which is called the relaxation time, is a function both of R and K. Also, there is one point yet to be mentioned. Now, let us imagine the situation. How the non-equilibrium distribution is attained and how it will come back to its equilibrium distribution. If we mentally think the situation, then we can see that once a deviation, I mean a pattern is set up due to the application of field, if that field is removed, then who will make it to reset? So resetting of the situation is driven by this scattering phenomena. It is okay. Now the question is, what type of scattering? Is it the elastic or inelastic? This is the question, and you have to answer that. So now the question is, what type of scattering? What type of scattering is responsible for relaxing back a non-equilibrium system to equilibrium system? Necessarily, it is surely inelastic. Not elastic, because when the system is deviated from a normal situation, some extra force, effort or energy has been given there. So in order to come back, there must have a process where energy will be redistributed, or from where the energy to be transferred to some other part. So when transference of energy is there, the process cannot be elastic. So it always be inelastic. So inelastic scattering effect make the situation to attain equilibrium. Right? So this much we can discuss at this point of time. Afterward, we shall talk about some physical consequences that arises or may happen under certain conditions that will be discussed. Of course, in relation to our the Boltzmann equation, the Boltzmann transport equation that we have already derived. Okay.